Hello and welcome. Welcome to lesson 2.1. So starting unit 2, we go into what is known as the derivative in calculus, and this will be a very large topic. We'll be on it for three units maybe, so it's going to be a biggie. The first thing we're going to do is introduce the general concept of it. As you can see in the topic, it says defining average and instantaneous rates of change at a point. So what is a tangent line? Examples of a tangent line drawn to a curve, f of x at a point P, and you're looking at 3 examples there. And it says, note, although many times we might say that a tangent line drawn to a curve may only touch the curve one time, that's not entirely true. A tangent line, by definition, is a line that can intersect a curve at least twice. So we'll see some examples of that occurring. So here's some misconceptions about the tangent line. Writing a formal definition of what a tangent line looks like is often problematic, though the following 4 misconceptions can be helpful when deciding whether a tangent line is tangent to a curve. So misconception 1, that the line to the curve, a line is tangent to a curve if the line crosses the curve at exactly one point. And we're looking at this picture, and while it intersects the line only at one point, line L is not tangent to the curve. Misconception number 2. A tangent line to a curve must cross the curve only once. Well, here we're looking at that P. I'm going to just put it in blue. P is tangent, or line L is tangent at P, I should say. But because of our function having some ups and downs, we notice that our tangent line, when extended, would indeed cross more, intersect more than just once. So it crosses the curve at 2 other points. Misconceptions about tangent line number 3. If a line is tangent to a curve, I'm sorry, let me try it again. A line is tangent to a curve if the line touches the curve at one point, but does not cross the curve. So in this example, they just stopped the line, made it more of a line segment. And that is not tangent. We can tell by looking at it that is not tangent. Although line L touches the curve C at a point, it's still not considered a tangent line. And then misconception number 4, a tangent line to a curve is a line that just grazes by the curve at a point, but does not cross the curve. Well, it can cross the curve, as we can see in this example here. Line L is definitely tangent to our curve at P, but it does happen to cross over the function that we started with. But yet it is a tangent line. All right, the little activity to take us into what is a derivative. So the tangent line problem. Begin with this graph of f of x. Step 1, it says, let us begin with an arbitrary point called c, f of c. As you can see by our graph here, we have that point. Then let's choose another point on the curve that has a horizontal distance of delta x from the initial c value, and we'll move towards the right. For now, let's call that new point x, f of x. Place this point on your curve, preferably close to the right edge. Connect those points, and then what is the slope of the secant line joining those 2 points? So we're going to put our point P way over here. It said place it over towards the right, and we're going to move our point x, delta x units away. So it's going to be, we're going to call this x, f of x. And right here we would have had x being c. Now where's my p? Somewhere about there. Here's my point P. We're calling that x. It is over to the right by some delta x. All right. Now connecting it up with a line. This is a secant line. And what is the slope of the secant line joining those 2? Well, to find the slope of this secant line, I would go into the slope equation, y2 minus y1 over x2 minus x1 to define my slope. And that slope then would be, the slope of the secant line would equal, I'm going to start with the highest y value, f of x, and then subtract the lower f of c value, divided by x sub 2 minus x sub 1, in this case, x minus c. And that would be the slope of the secant line. Step 2, it says, now, just for kicks, let's let our second x value from the above move closer to the original x value of c. Reposition that point so that it is about half as close to c f of c, and connect those points. Do we still see a secant line? All right, so we were about here for our first one. Let's pull it in a little closer. Let's call this our new point. So we had C, this will be X. Remember, we're moving it by delta X over, and we're calling this X, F of X. And now what would the tangent lines, or the secant, draw that secant line in, what would the secant line slope be? Well, the secant slope would be f of x minus f of c divided by x minus c. Do we still see a secant line? Yes, indeed we do. Secant lines, are a line that connect 2 points. So we've got that. And step 3, since we're having such a blast moving our second value closer to c, let's move that x value so that it almost touches c. Let's get it very, very close. And then we'll connect up those 2 points. And do we still see a secant line? Let's go with a blue. I'm going to get myself very, very close. We have c and x. And we can see here that delta x is getting much, much closer, or much, much smaller, bringing x closer to c. Is there still a secant line? Well, yes, because I'm still connecting 2 points, but that secant line is squeezing in. Once those points join together, then it's no longer called a secant line. Perhaps it'd be called a tangent line. Do we still see it? Yes, kind of barely, right? Because our x and our c are so close. How could we perceive the slope now using a very important concept here? What did it say in the bottom? Because I can't quite read mine. Very important concept from Unit 1. Well, we could write a limit equation on this, and I could say the limit as x goes to c of f of x minus f of c, that calculation for slope, x minus c, that this is the slope of the tangent line. Yeah, so if I were to continue bringing this point, my point C, very, very close, it would become the tangent line. So that's the idea, this idea of limit that we studied so hard in chapter 1 now assists us in defining the slope of the tangent line. So definition of a tangent line with slope of m. If f is defined on an open interval c, and if that limit of x as it goes to c is used when we have this quotient different, f of x minus f of c over x minus c, that gives us the slope of the tangent line. Then if that exists, then the line passing through the point c, f of c, with the slope m is the tangent line to the graph of f at the point c, f of c. The role of the different parts. What role did each of these parts play in getting us there? This really describes the change in y, doesn't it? Vertically, we had y2 and y1. X minus c really describes the change in x. This describes the slope of a secant line. And then finally, when we add the limit in front of it and we bring in x really, really close to c, then this becomes the slope of the tangent line at x equals c. Very good. I think you do not have those on your worksheet, but you may want to add those. Those could be helpful. Example 1, the slope of the graph of a linear function. So it wants us to find the slope of the graph f of x equals 2x minus 3 at the value x equals 1. Well, very good. Since I want to find the slope of the linear function, I'm going to use the limit as x goes to c. So, notation-wise, this is what we call a derivative. So I'm going to show you the notation for a derivative. It'll be f prime, and we're approaching 1, so f prime of 1 equals the limit as x, I want to be able to see, maybe I moved a little far. I want to see this. So I'm putting 1s in here for c. The limit as x goes to 1 of f of x minus f of 1 over x minus 1. And then let's bring our function into the mix, and we can say the limit as x goes to 1, well, f of x is 2x minus 3 minus f of 1. Putting 1 in, I'd have 2 minus 3 divided by x minus 1. I still can't calculate my limit because in the bottom I would have 0. So let's just keep proceeding forward. We get the limit as x goes to 1, 2x minus 3, negative 1, positive 1 over x minus 1. Looks like that can be simplified. So let's just keep motoring through. And I get 2x minus 2 over x minus 1 as x goes to 1. That limit, rewriting limit over and over, is extremely important. The limit as x goes to 1, factoring out a 2, I get x minus 1 over x minus 1. And then I can eliminate the factor x minus 1, especially from the denominator. And we can see here that our limit indeed is 2. So I can connect my notation. The derivative at f of 1 turns out to be 2, or the slope of the tangent at x equals 1 is 2. Now, is that a big surprise? Not so much, is it? Because we were working with a linear function, and we know linear functions have the slope in mx plus b style sitting right there in front of the x. So I knew all along it should turn out to be 2. I bet you did too. But we can show that our process of the limit approaching that point does indeed work. Example 2, the slope of the graph of a nonlinear function. Find the slope of the tangent line for this quadratic at the value x equals 1. Okay, so we're going to proceed just like we did. We're going to talk about f prime of 1 being the limit as x approaches c, so x approaches 1, of f of x minus f of 1 over x minus 1. That makes us have the limit as x approaches 1, f of x is x squared plus 1 minus plug in 1. I'd have 1 plus 1 over x minus 1. Right now we can't evaluate at 1 because 1 minus 1 equals 0. So I get x squared plus 1 minus 1. I'm sorry, minus 2, x minus 1. The limit as x goes to 1 be x squared minus 1. I'm just going to write x minus 1, x plus 1, the difference of squares. Maybe up here I'll go x squared minus 1. X minus 1, we get that factor to cancel, and the limit as x approaches 1 of x plus 1 turns out to be 2. In other words, my derivative, my instantaneous velocity at x equals 1 is 2. I don't think there's much else to say there. It's the slope of the tangent line. The limit equation that we've been working with is used so frequently that it's got a special notation, and we introduced that special notation, f prime of c, read f prime of c, is used to denote the slope of the tangent line to the function f of x at x equals c. Therefore, we can connect and have that notation attached to that limit process that we've been practicing. We will call f prime of x the derivative of f of x. Other common notations that are used are y prime instead of f prime of x, dy dx, or the derivative of some function with dx underneath. That dx underneath informs me about the variable that we're taking the derivative with respect to. Will definitely mean more as we go deeper into the calculus course. Example number 3, we're getting near the end here. Example 3, if f is a function for which the limit as x approaches negative 2 equals 0, then which of the following statements must be true? So if I have this, then I'm interpreting this as the slope of the tangent line at x equals, and I'm looking right there, negative 2, because that's my c value. And when these two when I'm coming to a value that equals 0 in my denominator, that indicates to me that I'm bringing my points very, very close together. The change of x is extremely small. So now, how does that map out to what they were asking? X equals negative 2 is a vertical asymptote. No, it has nothing to do with vertical asymptote for this particular setup. The function is continuous. No, I don't know continuity. Continuity, we need to know the limit and the value of the point and that they're equal to each other. Don't know that much information. The derivative of f of x at x equals negative 2 exists, or f is not defined at x equals negative 2. Not that. What we want is c, the derivative exists. Now the derivative equals 0, the slope is 0, but that's a number and it's just fine. Check your understanding. Let f of x equal x squared minus 4x. Find the average rate of change on the interval. This is the same as finding the slope of the secant line, which we have been doing earlier. So f of x equals x squared minus 4. I want average rate of change. Sometimes that's referred to as AROC. So I'm going to use that simplified version of it. And what I need for slope is I need to evaluate f of 5 minus f of negative 2 divided by 5 minus negative 2. y2 minus y1 over x2 minus x1. Write it down if you must to help you remember it. Okay, so our AROC would equal, we got to plug in 5. I'd have 25 minus 20. Take away, put in negative 2. I'd have 4 plus 8 divided by 5 plus 2. And Let's keep working forward. What do I got? 5 minus 12 over 7. And that gives me a slope that's equal to negative 7 over 7, which is negative 1. My average rate of change is negative 1. For some reason, I keep looking at my notes because I had 6 as the denominator, but 6 definitely isn't the denominator, 7 is. All right, find the instantaneous rate of change at x equals 3. Instantaneous rate of change means find the derivative. So we want f prime of 3. We're going to use that limit definition as x gets closer and closer to 3. So let x go to 3. And then we'll have f of x minus f of 3 divided by x minus 3. Okay, rewrite the limit as x approaches 3. F of x is x squared minus 4x, correct? That's our function. Take away, set up a parenthesis because it's going to have a couple terms to it. 3 goes in and gets squared, that makes 9. 3 goes in, multiplies by 4, that's 12 over x minus 3. You can fit one more calculation here at the bottom. I am looking at x squared minus 4x. That would be negative 3, but negative 3 makes positive 3. Okay, that looks right. X minus 3 on the bottom. I still cannot plug in 3 because I'd have 0 on the bottom, so I'm going to keep trying to factor here. So f prime of 3 equals x minus 3, x minus 1. Excellent. Oh, darn it. You know what I forgot to do? I forgot to write my limit. So let's see if I can move this stuff over a bit. That will work. Limit as x goes to 3. Now we can see very clearly that x minus 3 cancels with x minus 3. And now we're calculating the limit as x goes to 3 of x minus 1. Plug in your 3. 3 minus 1 is 2. F prime of 3 is 2. The tangent line slope at 3 is 2. All right. 2. Write but do not evaluate an expression that gives instantaneous rate of change. Well, we don't have to evaluate this one, so it'll be a little bit faster. We want to be at 2. Our function is g. So this time it'll look like a g prime of 2 is equal to the limit as x gets close to 2 of g of x, I'm just going to write the general, minus g of 2 over x minus 2. The limit as x minus 2, our g function is negative 1 over 3x. Plug in 2 and I'd have negative over 6 x minus 2. How fancy do you want to get? I think I'm going to call this good. This is an expression that I don't have to evaluate. So good enough. 3, which of the following gives the instantaneous rate of change of f of x at x equals negative 1? Choose all that apply. I don't want h to be going to infinity. That would give me end behavior and help me find horizontal asymptotes. As x goes to a, no, that doesn't seem right. As x goes to negative 1, this has got some potential. It would be x minus c, and this is my c, isn't it? So this really should say x minus negative 1, so nope, not liking that. As h goes to 0, and I have f of negative 1, f of negative 1, this going to 0, that would bring my points very, very close together. I'm liking that one. As h goes to 0 of f of x plus h minus f of x. Um, yeah, that seems fine too. Oh, but that's not going to find it for me. That's going to give me the general derivative. That's going to be all in terms of x's. I think we got to back that off. This is close, but doesn't help us at -1. But it's not at x equals -1. So for that reason, I'm not going to circle it. How about this next one? This is what we needed to see over here. Yeah, this works. This looks good. As we go to -1, we have just h. Well, then that would put -1 at the bottom, and I want my x's to have a difference close to 0. So that one I'm going to rule out. What's with this f of a? Yeah. So there's those. All right, that is the lesson. You have a Delta math assignment to go through. It has 7 questions. So good luck with that.